Right. So I have these things open, but I also have them printed out. And the first thing I would like to go through is the string manipulation. The very good thing in this cheat sheet that I don't know if I can zoom in. Yeah, I can zoom in a little bit. That it's very nicely uh, a nice graphic representation of what is happening. So if you have what you have here always on the left hand side is a vector with different strings inside, and if you look for the just to see if there is your pattern, there is your substring, there is your letter within the string, then it will give back this kind of result. So if you have that pattern in the first, second, and the fourth one, but not in the third one, str detect will give you true, true, false, true, while str which will give you 1, 2, 4. We will use this one later, so you will see how we can use this. And of course, all the others will give you uh, what you can see here. And of course, it's not just working on vectors, but as usual, it is because it's R, everything what is working on a single variable, like a single string, a single sentence, or a single sequence, the same kind of thing is working on a collection of sequences if they are in a vector. So very important things are how we can detect, how we can subset the strings. We will use this one as well. I actually don't really use too much length management. The STR length is, of course, very, very important, especially if you are working with sequences. That's the easiest way to find out how long is your sequence. You have to be very careful with the mutate columns here, and also when we will discuss the data manipulation, because this is always changing your data. What you do here, you always keep your data intact, and you just extract something, you just check something on it. But if you use the mutate, you will change your data. So that's very important. Split and join you will use a lot of times if you want to print out your results and you don't want to print them in everything in a separate line, but you would like to use, for example, a CSV format, which is a comma separated values format. And you can use comma to separate your fields and print out. And the same way you will use split a lot of times as soon as you are processing any kind of tabular format or any kind of like CSV format, you will use the split very often. We will do this today as well. And of course, ordering is very important. The regular expressions, we will do a few, but I strongly suggest to try to ask your own questions. So if you go back and sometimes in your past you had to find specific promoter sequences, promoter patterns before a gene, or you had to find a specific protein sequence pattern, for example, a glycosylation site or a phosphorylation site. Go back to those and try to do it yourself. I will give you a few guides today, but it's again the best if you can do it your own. But you will see the regular expression in action today. It's a very important thing. Before we start doing anything, you have to have these things installed. So if you don't have stringr installed, then you can go on the packages tab and push install, or go up and say tools install, but that's maybe the easiest way. Install and say string r and just push install. I have it already installed, so I won't do it again. Yeah, I will do it again. And we also open a new R script. And because we will work with the stringr package, we also have to load it into the environment. So what we have to start, as always, is saying library and stringr and push command enter or control enter. I will wait a little bit just to let enough time to everyone having the package. Where is my chat window again? Okay, it's here. Right. And the first thing what we will do, we will download a protein sequence, and we will do a few things with the protein sequence. The easiest way to download anything from the internet, especially if it's a text-based thing, is using the scan command. I think that's a basic, that's in the base. Yeah, so it's actually open for me. So the scan command can go through any kind of file and read in its content. So what you have to do is to go up to uniprot.org, and look for any kind of sequence. What I will download is an antimicrobial resistance gene called BLAT and underline equal LX. So it's a beta-lactamase gene. Again, it's BLAT underline equal LX. This is what you have to write into your search field. And the way how we will download it is we will click on format and say FASTA. So you will have only this FASTA file here. And you don't have to download or copy or paste. You just have to copy the URL, which is hopefully here. I have my Zoom header here, but hopefully, so just copy the URL from there and go back to your R and say scan. And in double quotes, put in the URL you had. It won't work, but it's okay. The problem is, you can see here, if you hit command enter, it says that there is something, the scan expected a real is a real number. So it's expected a number in in the file, but there is no number. It's much more like a character type or string type. So if you go on the description, on the help description of scan, what you can see is that, of course, you have the first argument for the scan command is always the file, which can be a file path in your own computer, or it can be a URL. And the second thing is what. And if you look at what means, that means what is the type of the data you are reading in. And if you look at here, always the under the usage, if you say anything, if you see anything here after what, if it's not like what equals to double quotes, but if you see what equals to double, that means that there is a default value for scan. So in default, the scan command try to read in the contents of a file as numbers. Is there a problem with someone? I just hear that someone turned on the microphone. Is there any problem with installation or downloading? Okay. If not, then we are going forward. So what we have to change is that we want to read in the contents of this file as a string, as a character. It is called character in R. So what we have to do, instead of just saying scan and the FASTA file name, we have to say what equals to character. And so the same kind of way as double here, we will read in as a character. And this is working. So this is how it was read in. It's not perfect yet because it's not really what we want. I would be happy to see the first line, which is the FOSTA ID, in one line, in one record of a vector. So it gave us back a vector with 14 elements. And the very first line, which was this, was separated by all white spaces. So this is also what you should learn as a term in programming. Programming, you call this as a white space, because white space can be anything. White space can be one space or three spaces and two tabs. So anything which is, it looks like a hole or a gap is a white space. In this case, this is just the spaces. So it will separate the first line as well. Here, 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 and here. And of course, all the other space. And also it will use the new line character to separate the string. So the first one we have to do is to ask the scan not to use the white space as the separator. And if you look at the help again, there is an option you can use, this one here, separator, sep equals to anything. So what we have to do is only say that I want to use the new line character as a separator, and I hope you already know what is new line character. It is the \n. In almost all programming languages, \n means a new line character. This is how you start a new line. This is how you will export your data. If you make a table, at the end of each line, you just print out a \n. So if I run this, then you already see what we really wanted to see, is that we have our ID in the first line, and then we have the sequence content in the following lines. So let's put this into a variable, saying FOSTA record. Of course, you can also click on it now from here, and you will see. Now you cannot click on it because it's just a character vector, so it's not a data frame yet. Okay, but it's a vector. It's the same what we have here. So if you say FOSTA record, then you will see the same content. So let's look for sequence patterns in this sequence. The first problem is that we have something else than the sequence as well. So in the very first line, or the very first element of our vector, we don't have sequence, we have the ID. I don't want to completely get rid of this because it's important, but in terms of looking for a sequence pattern, we don't need that. And the other problem is that if you looking for a sequence pattern which is on a boundary of two lines, so if you are looking for FRP EER, of course, R won't find it because it's in real life, it is a sequence which is in one piece, but at the moment in our vector, this is in two different cells, in two different parts of the variable. They will never will be read as one line. So what we have to do, we have to do two things. I would like to have a variable which contains the sequence itself without new lines, without spaces, just a sequence, and without the first line. Okay, let's go to your RString cheat sheet. So what do we want to do? So first of all, we would like to do something like this, detect matches, because there is a characteristic difference between the lines that are containing sequence and the lines that are containing the ID. And this is this ID sign, which is always there for the FOSTA ID line at the beginning. So if we have a line with this in the beginning, that's not a sequence. If we don't have it, that's a sequence. Okay, so if you just say something like Str Detect, let's check it, and we can put it here, Str Detect. For this, of course, you will need the string R loaded already. Str Detect. Let's see how we use the Str Detect. You have to put the string as the first argument, and you have to put the pattern as the second argument. The first thing is our FOSTA record. And again, it's not one string, it's a collection of six different strings. And what we want to look for is the FOSTA ID. So if you run this, what you will see down here, you will get back true, false, 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 false. So we have it only in our first element of the vector. You can be a little bit more specific. Sometimes you have, I mean, in Quantifiers, you shouldn't have this sign anywhere else. You shouldn't have it in your sequence because it's not a protein or DNA sequence. But just to be completely sure, you can use this sign here. And if you go to your cheat sheet second page, or if you are going to your regular expression cheat sheet, then you will see that this sign means it is here, it is the encore, it's called encore. So if you say this, then the pattern you are looking for has to be in the beginning of your string. And this is what we actually have here. This is always in the beginning of your line. But in this case, it's not that important because we shouldn't have this sign in anywhere in the sequence. But this is a good way just to memorize it. That if you see something like this, it means that I have this kind of sign at the very beginning of the line. The opposite thing, as you can see it on the cheat sheet, is the dollar sign. So if you put the dollar sign there at the very end, that means that the pattern you are looking for is at the end of your, it's actually the last character of your string. We will practice this a little bit later as well. Okay, so this is not bad. Now we know that, okay, our first line is the ID line, and all the other lines are probably sequence lines. But what we want to do is much more extracting those lines which are the sequence lines. So we would like them to be true and this to be false, or especially if you go back to your cheat sheet here, you would like to do something like this. So we would like to have the IDs, the indexes of those lines which are containing or not containing our string of choice. So let's just use the str which instead of str detect here. With the same FOSTA record and having the FOSTA record sign in the beginning. So what you see now is the give back us 1, which is the index of that line which contains this string. But we actually need the opposite. We need those lines that are not containing this sign. Let's go to the cheat sheet and try to find that thing which is the opposite. And if you look at here, it is under the alternatives. So what you see here, it will be a little bit confusing because we are using exactly the same thing what we are using as the indicator of the beginning of or start of the string, but we are using it in a different context. So what you see here is if you use square brackets and you put in the pattern you are looking for, but you start your pattern with this rooftop sign, then it will look for all patterns which are not anything but this thing. So let's just translate it here. So I'm using this. If I'm just doing simply this, the result will be exactly the same. We will have the one. But if I'm using the rooftop inside the square brackets as well, so what do I say now? I want to look for all the lines which are starting with anything but not this sign, okay? Starting, this is for starting, and this is anything but this thing. So if I'm pushing enter, command enter now, as you can see, it's 2, 3, 4, 5, and 6. So all the lines which are containing the sequence. Okay, perfect. So now we know what are the indexes of those lines which are containing the sequence. So here we finally know where the sequence is. So as I said, we would like to put them together to one string because we want to search for specific sequence patterns, and we also want to include those parts of the protein which are actually in new lines and which are broken by the new line character. Let's go back to the cheat sheet and see how we can join strings. And this is exactly what we have here. So we have multiple lines of data, multiple records in a vector. And what we want to do is to combine them to one string. So what we will use is the str underline c. And we also have to use the collapse. That's very important. The collapse will collapse them. So what is happening if I say strc record collapse equals to just this. So if I do this, we have all the information into one string. It's now nicely just in one string, but we have the ID line as well in the beginning. So we have to do the collapse on just a part of the FASTA record. And this is when a little bit of programming will come in. So these are, just let me say here, we have the indexes of those lines. If I want to show you the first line, as you may remember, if you have a vector and you want to print out the first element, you are doing this. If you want to print out the first and the third line, first and third element, and you can use 1, 3, no. 1, and this is how MATLAB do it, but I'm not sure if it's no. Okay, so if you want to print out the first 3 lines, you can do this. I think, yeah, I know how to do it. You have to give it in a vector. So you have to say C 1, 3. And by this, you are defining a small vector with 2 elements. 1 is the first and 3 is the second element. This will be given as the indexes or indices for taking the 1 and 3rd line from. And if you look at this, this is really not the 2nd but the 3rd line of our FOSTA sequence. So what we have to do is we have to use str which to find out which line we want to print out, and then we have to use strc to join them together. So what we are doing here, it will be strc. This will be the final command which will put the line together. But instead of saying FOSTA record here, just simply FOSTA record, we are saying FOSTA record, and here we will have to write in the lines, and then we are saying this collapse. If you want to do it manually, then you just simply say C, it's like it was here, 2, 3, 4, 5, and 6. 2, 3, 4, 5, and 6. And it's nicely putting into all the sequences into one string. But this is not really nice, not really neat. You shouldn't do this if you are doing programming. So what you do instead, I will leave it there, but saying that this is nice and especially not replicable. So if you download a different sequence which is much longer or much shorter, then of course you will have to include less or more lines. So it won't be always the 2nd, 3rd, 4th, 5th, and 6th line. So what you have to do, instead of stating exactly which lines you want, you just put in this. We use this command to detect which are our sequence lines. So this one will give back in default a vector, a character vector with the numbers, and that will be used by R to select only those records from the vector. So if you run this, then you will have the sequence nicely. So let's just put this into a variable called sequence. And now we can do our string searches. What we will use, we don't use detect matches. What we want to really do is to find and print out the matches, which is str. We will use the str replace as well. But I think there's an str match. Yeah, this one. So this one will give you back the patterns, the matchings as well. Why this is important. Okay, so let's just first say that how many double leucines we have in the sequence. This is just a count, str count. In many cases, you just want to know how many G's and C's you have if you want to make a GC content of the sequence. So you can just, of course, it's not a DNA sequence now, it's a protein sequence. But if you want to say like number of glycines, then it's just simply str count. You are putting, how do you call it? You are putting your string as the first argument and the pattern as the second argument. So what you will do here is we'll put sequence here. Okay, the sequence is actually a built-in command. Yeah, let's use something else. Okay, let's just simply say sequence with capital S, and this is quite enough. Oh, yeah, that's true. Okay, then, okay, let's just use S, E, and Q, but with capital. Okay, and rerun this line then. Yeah, I know that there was some mistyping as well. So I will use this as my string, and I'm looking for G's. This is the single letter code for glycines. And if you run this, and then you want to show how many glycines you have 21. So that's very easy to calculate G's or C's. If this is a nucleotide sequence and you want to calculate a GC content, so you want to count how many G's and C's you have, and then you can do this. This will be, of course, this is a protein sequence, but we have C as well here, which is the cysteine. So num-GCs, instead of saying this, the problem if you say this, it will look for GC. I mean, this dinucleotide or dipeptide in this sequence. So I don't know if there is any GCs in our sequence. No, we haven't got any, but we don't really want to look for C after G, but we want to look for all the G's and all the C's and count them. And this is when you again use your square brackets. So what this means that you are only looking for one character, but that one character can be G or C or anything else what you write here. So as soon as you run this and you look num-GCs, it's now 24, which means that there are probably 3 cysteines right next to the 21 glycines in this sequence. Okay, but this is the same kind of thing which is working for a GC content calculation. How do you calculate the GC content? GC content. Again, this is protein sequence, I know, but you can also calculate the percentage of G's and C's in the protein. There isn't too much rationale behind it, but I'm trying to make this program a bit more universal for protein and DNA sequences as well. So the content is actually the number of G's and C's together divided by the length of the sequence. So you can use the same here, what we have here, or just simply say num GCs, because we already calculated the number of GCs, divided by, what was the length? It was the str length. This is what we have to use, and just simply put the string as the argument. So what we say is str length. And here the sequence. And run. And then we have a nice number for GC content 8.4%. What is happening if you would like to look for a bit more sophisticated sequence pattern? Let's look for just double L's first. So now we are not looking for one leucine, but we are looking for two leucines right next to each other. Let's first count how many we have. Str count. In our sequence string, we are looking for LL. So now what I'm doing is I'm looking for exactly this pattern, not an L or an L. It's not in a square bracket, but it's a double L. And if you look, if you run this, then you will see that we have 5 LLs. If you say str extract, it will be extracted. Of course, it's not really surprising that if you extract an LL, it will be an LL. There is a huge difference here. Str count is counting how many LLs we have. Str extract will extract the first instance of LL in our sequence. So we are actually losing 4 other. Luckily, if you look here, the str extract has a child function, which is called str extract all, which will extract all the instances of that pattern you are looking for. And of course, it's not, again, very surprising that all the instances will be LL. But what is happening if you look for an LL, but after the LL, for example, this is it won't be a recognition site for any kind of phosphorylase or phosphatase or glycosylation enzyme. But if it's, let's say that if it's your enzyme recognition site, and you know that, okay, I have to have 2 leucines, and after that there should be a negatively charged residue. But of course, R is not, doesn't know what is negatively charged residue. You cannot say that. Let me just copy this and then putting here something like, you know, like negative. I mean, you have to define what is that. And this is when, again, the square bracket will comes in. So you will put in all the negatively charged residues here, which is actually the D and D, so the aspartate and the glutamate. So you are looking for patterns now, which is LLD or LLE. Let's see if we have any. No, we don't have any. Let me just try another. Okay, let's go and look for a double L, but it is now followed by a residue with a hydroxy group, which is threonine or serine. So what you see now, we have 3 LLTs actually in the sequence. This is one is here, and there was also one here. Of course, if we would have any LLS, which we don't have, it would be here as well. So with this kind of pattern, and we are now going more deeper in what is really the pattern, it is now interesting what is actually the match, because you don't know what is. You just look for double L and then something which is a hydroxy group. So the next thing, if you want to look for the surroundings, this is again happening many times. For example, if you look for a specific promoter sequence, you want to know what's the sequence around. If you look for a short motif in a protein sequence, it's not too bad to know what are the flanking regions, like the 5 residues before and 5 residues after. How can you do this? Okay, let's first just copy this, paste here. If you just put a dot here and you put a dot here, that means in regular expression, anything. This can be anything, really anything. Space, letter, number, sign, anything. Dot means anything. If you want to look for dot, specifically dot, then you have to use an escape character. So this is how it's working. Dot in its own means anything. If you want to look for dot because you are looking for dots in your string, you have to use \\\. Don't ask me why are using double backslash as an escape character. Every other programming language is just using a simple, this is what you see in the middle column here. This is how you should define dot in Perl, Python, Julia, and every other programming language is also in command line, but in R is using a double backslash for so-called escaping character. But now we want to see the surroundings, so we would like to extract that pattern, that part, which is containing a double L, then a T or S, and also we want to see the two flanking residues, one from the N terminal and one from the C terminal side. Okay, so as soon as you run this, you already see that this is only what we're looking for in the middle, LLT, 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 but you see what is happening before and what is happening after this short pattern we are looking for. And now again, this is why you want to extract a pattern, not because you want to see again what you write in, but I didn't write in LLLTT or KLLTG. I only say that I want to look for LL and then a T or S and the two flanking residues. If you want to look for a longer flanking region, you can just simply repeat the dots, but this is again not really nice. So you can do this. So if you want to look for 5 residues, then you just put 5 dots here and 5 dots here. Again, not really nice, but it's working. It's much longer now. The reason why we don't have the first one, I think, because it was in the very beginning of our sequence. So if we go back to the sequence, probably there is nothing before that. Oh, it's actually not. Oh, no, it was in this one. Oh, yeah, this is probably at the very end. No. Interesting that we don't have 3 here. So we have this one. And we have the KLTG, but we don't have the ELL. Oh yeah, I know why. Because it's actually within this string as well. So from now, this won't be a separate instance anymore, because the first one, which is the KLLTG, is going forward with the 5 dots after that, and it will. So there is, if you are extracting regular expressions, they cannot overlap. Actually, the second one ate up the third one now. But as I said, this is not nice. What you want to more do is you have to quantify how many dots you want to see before or that, or how many residues or how many nucleotides you want to see. This is also very useful if you, for example, looking for promoter sequences and you know that your coding sequence starts at position X, and you know that you are looking for a specific pattern within a range, let's say 5 to 10 nucleotides before your starting position. then you will also use quantifiers. You can use exact quantifiers. This is what we will do now. So what I'm doing is, now I will copy this one. Someone has the microphone turned on. Again, I can hear someone. But instead of looking for only one, and like again, let's go back to our cheat sheet, how we can quantify. This is how we can quantify things. If you say star or plus, the star means that 0 or more, the plus is 1 or more. We don't really want to do this. We want to say exactly how many times. We want to extract 5 nucleotides before and 5 after, or residues. So we have to put the number into curly brackets. So we want to say see anything, 5 from anything, and also here 5 from anything. So the quantifier is always quantifying the thing which is right before it. So it's not quantifying this one. We don't want to see 5 LLs. We want to see 5 anything, then LL, then T or S, and again 5 anything. Okay, so if you run this, it will give you exactly the same results as when we wrote the dots together. What is happening if you want to extract something, and I think it will come up from one of our data sets. So let's just read in one of our data sets from last week. I will use our last week plot, and I will read in, I think, the not the replica exchange, not really this one. Okay, it's not there. I think it was the one which I sent you in my last email. So what I would like to read in, it's on my desktop, hopefully, is more the read counts, or much more the plasmid, one of the plasmid files. Okay, let's read in this one. The plasmid connections. Oh, you don't have this. You have the plasmid connection with longest txt. Let's read in this one, just with the simple import data set. There is no header, so we are just leaving it the same way as it is. So we will use V1, V2, V3, V4 as the column headers. It will be imported into this plasmid connection with longest. Let's just reduce the length of this variable name. Otherwise, we always have to write it out. Let's have it as plasmid underline con and import. Okay, so we have it here. So what you see here are node identifiers, especially here, but also these are assembly identifiers for our metagenomics data, from which this is the C09103, for example, for the very first record, is the identifier of the sample, which means it's a chicken sample. It's coming from farm 9. It is coming from time point 1. And in time point 1, this is the third sample. And it's in clade 00029. And this is actually just the size of the sequence or the assembly. So what if I would like to extract all the clade identifiers from here? So I cannot really, in this case, I would be able to use the position, and we will use that as well. Okay, let's do it first with just the position, because as you can see, the clade identifier always starts at the very same position in the string. The string before is always the same length. So what we have to do, we are now extracting a substring. So let's go back to our cheat sheet. And we are doing something like this. So we have a string. We would like to find a part of it and extract to a new column in our data frame. Again, because we are working with R, we can do it on the whole column at the same time. So we will use the str sub. What do we have to give for the str sub? Of course, we have to give the string as the first argument we want to work on. And then we want to give the start and the end position. What are these 1L and minus 1L means here? The 1L is very important. This is again a bit different in different programming languages. String position starts in R with 1. So our first character, our first C, has the index 1. In many other programming languages, string character indexes are starting with 0. So the index of this first C would be 0. But in R, which is much more closer to, I think, to our thinking, this is the first character, second, third, and so on. So how we can extract the clade identifier, just the clade identifier, so just these 5 characters. So what we will do, let me just put this plasmid connection reading here. So what we will do is extract these numbers by position. So we just have to count, where is it? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, I hope, but maybe it's not 16, we will see. So if this underline is the 16th, then this is the 17th. So we will start with the 17th, and then 18, 19, 21. Let's see. So the command was... Sorry? Oh, it's length, it's not stop. Okay, no, it's end. Can you do a length? I don't think with the str sub you can do. No, I don't think so. In many programming languages, I don't know if that was the question or the comment I got, because I just heard the half of it. In many programming languages, you have to give the length, but in R, you have to give where it starts and where it ends. Not the length, I think, but we will see. So our string is now the plasmid connection file, and not the whole data frame, but only v2, which is our column with the assembly identifiers. And we would like to extract from 17 to 21, maybe. Let's see. Oh yeah, this is it. So we extracted all of them. But the problems come here. Let's check what is the type of our v2. Is it a character or a factor? It's a factor, which means that we probably have to handle this as a factor as well, or we have to handle as a character, or actually this is not it's none of them. It's much more like a number, but it's not really good at number. Okay, let's just handle it as a factor. The reason why I want to handle it as a factor, because it's actually repeating many times. So we have an assembly from farm9 time point 1 simple 3 in clade 50, but we also have other assemblies in clade 50. So we will be able to subset our data set by the clade number if we are handling it as a factor. So what we did here which I don't really want to do here, but much more in the R script, in this one. Let's just put it into a new column in our data frame. So what we do is we are putting into plasmid connection clade ID. This will be the column identifier, and we are putting into this one our clade identifiers, which is a substring from the same data table. So if you say enter, now you have a clade ID here, and it is a character vector, which means that every cell is eating up your memory, which you don't want, but you would like to handle it as a factor, and then as a factor you will use much less memory. So just simply you can have to say as dot factor here. And if you push command enter, you can now see that clade ID here in your global environment. Now the clade ID is a factor. It only has 347 levels, which means that we only have 347 different clades. But actually, if you see the amount of data, we have almost 12,000 entries in this one. So we are using much less space. Okay. The problem here, yeah, let's open the other file, because this is just how you do the substring. But what I really want to show you how you can extract a string by pattern match, what we did here. But if you don't know what is the string you want to extract. So let's open the other file I asked you to download, which was, I think, was it the plasmid coverage? No, 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 no. Let me check the email. Oh, I cannot check the email. Let me check the Google Drive. I think that was the longest real plasmid fragments txt. Is it on my desktop? Yeah, okay. Yeah, this is it. I hope all of you have this one as well. Again, we don't have any headers in the file, so let's just leave it v1, v2. So let's just let the heading know. So what you have here, and this is what I wanted to look this file, because we have this v3, this third column, where we have identifiers. This is very common if you are using spades or metaspades. The contigs that are assembled will be named like this. They are called nodes. They will have a number, node number, and then length, and here's what you have as a length, and then cov, which means coverage, and this is the mean coverage of that, the sequencing coverage of that particular config. So let's copy this again to our source code. So what I want to do now is I would like to extract the length and put it into another column. We already have it here, but don't look at that at the moment. And I also want to extract the coverage. As you can see, now we cannot really use the position, because for example here we have that many characters before, because the node identifier a 3-digit number, but here it's a much larger number. So we cannot use the position that I want to extract position from here to here and from here to here. So we have to use something else. I also don't know what is the length and what is the coverage. So I cannot extract by saying I want to extract 20.928181 because it's working for the first string, but it won't work for the second string. So what I have to do is, luckily we have strings that are always there. So what I will do, I will extract that thing, that string, which is between length underline and underline cov. And then I will extract that part of the string, which is between cov underline and the end of the string. How does it look like? I will leave it here, and I will write it here because it's easier a little bit. So what we are doing now is we can do with the I think it's str match what we have to use here. I hope. Yeah, I think so. Str match. So let's just first try to extract this thing, this whole thing, without the node thing in the beginning. Okay. So the variable or the string we are working on is called longest very long file name, but luckily we can push the tab, which will help us to autocomplete. And now we need the pattern here. So the pattern is, there is a word length and the underline. There is something after that. We can say just dot plus, which means that anything more than 0 times, and then an underline, and we have the cov as a coverage. Underline again. I'm just simply copying everything what is here, but leaving out the spaces for length and coverage. And again, we have here dot plus. And something is not right. Oh yeah, the problem is that I'm doing it on the whole data frame. I just want to do it on the v3 column. Here we have the v3 as the identifier. And we have a lot of strings, and we have what we want, but we actually want the numbers here and the numbers there. Okay, how do we do this? The way how you do is you can use something which is called grouping or groups. This is again, if you go back to your cheat sheet, not this one, but the strings. It is on the second page down here, groups. So if you put the thing what you really want to extract into normal brackets, then it will be handled specifically, and it will be extracted separately as well. Let me show you how. If I put this into brackets, so which means that I want to separately extract everything which is between length underline and underline cov. I just put it into brackets. And if I run this, now we have a vector that has 2 columns. It's a matrix now, because we have 2 different columns. We have the whole match here, but we have our specific thing here. Someone please mute Rakshit. Please mute your microphone because it's I can hear it. It's not good. So as you can see, I didn't say that I am going for a number which is 40041. I'm just looking for the thing which is between length and cov. This is very important because you will use this many times. As soon as you have identifiers, as soon as you have sequences, you don't exactly know what you want, what you have inside that part you want to extract. You just know what is the surroundings. This is, again, this can be a sequence as well. You have two primer sequences and you want to extract from the sequencing what is between them, or you know what is your Tradis, how do you call that, the transposon sequence. And you don't really want to extract the transposon sequence from the Tradis sequencing, but you want to extract what is after your transposon, your known sequence or your known primer sequence. And this is what you will do again. You will put your known sequence here, and you will say that I would like to extract everything what is after that. And I actually don't really want to bother with my primer or a transposon sequence. I just want to know what is after that. So what you have here now is we have that extracted thing in our separate column here. And you can also do this with the coverage. So you can do this now. And what will happen is you will have a matrix with 3 columns. Now, the first one is containing the whole match. The second one is containing your first target sequence. And the third one is containing your second target string. So how can we put them in to here? I was trying to do this in one step, and probably it is working in a way. I'm not sure if I can do something like this. I don't think I can do something like this. Can I? Oh, yeah, I can. Okay, then I can do it. So let's copy this here, and we will make a new column in our longest real plasmid fragments. We will say that let's make the config length by extracting these things, but only using all the rows, but only the second column. If you have a matrix, what we had here we have a matrix. If you want to print out the first element here, you have to say the matrix name and then in square brackets 1, 1, which means that the first row, first column, this is 1, 2, first row, second column. If you want to print out all rows in column 1, then, or column 2, this is what you use. So you don't specify the row name, you just leave it blank, say comma and say 2, which means that it's the second column of our matrix, but all the rows. And now, if you go back to your longest real plasmid fragments, we have a config length column now, and you have your data there. Again, if you have your sequence in your data frame, you can put your specific sequence pattern here. If you have your FOSS-Q row sequencing here and you want to extract that sequence part, which is after your primer or between your primers, then you just put it in a different column here if you want. And also with the same way, if we want to put our coverage, let's just say cov coverage here, then we will use all the rows, but only the third column from this matrix, what we made with the str match. And now you have all the coverage values here. And because it is an interesting data, let's go back to last Thursday, load in ggplot library, just to have some rehearsal, some repeat ggplot. 2 and plot the config length against the coverage. So saying that I'm using ggplot, I would like to use the longest real plasmid fragments data frame. I'm using the aesthetics for the x axis. I would like to use the coverage value. For the y, I would like to use the length, which is config length. So here you are only giving the column identifiers again. And I would like to do a scatter plot from this. So I will use the geom point visualization, which is a scatter plot. And if you do this, then you will see a nice plot. There are problems here. There are several problems here. So first of all, the coverage values are looking awful. And also the config length is a bit strange. Why do we have the length in a alphabetical order, not in numeric order? It should be an x. It should be a y-axis, which is a continuous axis. The reason is that when we do the extraction here with the str match, because we are getting back a matrix. This was this matrix which we had here. This matrix. In this matrix, we have at least one column that contains character type variables, strings, letters. And because matrix can only keep the same type of variables in it, for this reason, the numbers, which are actually numbers and numeric types, they were extracted as strings or character types as well. So if you look at your longest real plasmid fragment data frame, both config length and both coverage are character vectors. And this is why ggplot is arranging or ordering them alphabetically. So what we have to do, we have to go back to our extraction, and we have to put this whole thing from here to there into brackets, normal brackets, and convert them to numbers. So we have to say as numeric. And with this, it's already changed, and the config length here is now a numeric thing. And we also have to do the same. Anytime you see a ggplot or a plot which is strange, which is not correct in the way how the numbers are looking or your axis, then it's always because your variable is not in a good type. Maybe it's a factor or maybe it's a character type. Then you have to go back and you have to reassign these values to the columns. And now the coverage is numeric as well. And if I'm plotting now, it will be much nicer because we have a normal x and normal y-axis. And what you can see here is that one of the graph I showed yesterday for many of you on the Big Lab meeting is that most of our contigs which are containing our target plasmid sequence, what we are looking for in this metagenomic sequencings, are having a reasonable size. We know that the whole plasmid sequence is about 45 kb, but in this case, we usually have at least a 40 kb continuous fragment, only getting smaller if it has a much lower coverage. Let's make this graph nicer. Again, I'm speaking too much about strings, but I want to make this nicer just to show you how you can make it nicer. So first of all, let's replace the X and Y axis labels because they are not really nice to publish. So let's have the X lab coverage of the config, and the Y lab, which is the Y label, is length. Length of config. Okay, it's much nicer now, but it's a little bit small. So let's just make them a bit bigger. And this is what we did with the theme layer on our ggplot. And we are saying axis dot title. It's not label, but title. This will be an element text. And the size should be 14. So it's now much bigger. Let's make it bold as well. This equals bold. Make it more emphasized. Nice. I think these numbers are small as well. So let's just make. Let me check if. Sorry, my chat window was not here, so now I can. Can you also use pattern recognition as a start and end point? We will go back to this question. You can extract the, yeah, I think the position you can. This is the str locate. We will find this soon. Okay, so let me just make the numbers are bigger as well. So this is axis dot text. And let's have it like size equals to 12. So now they are bigger as well. And I think I can make a bit more conventional theme. Okay, you have to put this before your modifications on your sizes. So it's now a bit nicer. It's also possible to fit a line on it, but I think it's maybe the geom smooth. Let me just skip that for now. Okay, so yes, you can also use pattern recognition to find where is it in the sequence. And I think if you go back to the cheat sheet, I think this is what the str locate used for. I think it will give you the start position. So if we go back to our double Leucine example here and say str locate sequence and this in them. Then you will have positions here, 135 and 139. We should have 3. We had 3 before. Okay, again, I think it's because there is an str locate all. Okay, so what we have here now is the start and end position of the first instance. And if we are using str locate all, and by using exactly the same thing here inside, then I hope we will get back 6 numbers. Oh yeah, so now we are getting back, I think this is probably a data frame or a list. Let's check it. If you don't know what is this, then you can always say, so this comment will give you back something, but you don't know if it's a data frame or a matrix or a list, then you can always say type of, and it's a list.